Hi guys, and welcome to AP Calculus BC Sequences and Series. Today we're going to be talking about Taylor and Maclaurin polynomials. By the end of today's lesson, you should be able to approximate functions with Taylor and Maclaurin polynomials, as well as find Taylor and Maclaurin polynomial approximations for elementary functions. We're in section 9.7 in the book if you want to follow along in the book, and everyone should be working on their Sequences and Series homework packet. Suppose I asked you to approximate e to the 0.1 power. How would you go about trying to answer this question? What if I asked you to approximate this to 0.0001 accuracy? That becomes really difficult if you think about it. You may be able to approximate e to the 0.1 power, but you're not going to be able to approximate it to 0.0001 accuracy. In the past, we were able to approximate values using tangent lines and linear approximations. If you recall, all we need to do to create an equation of a line that will give us an approximation is a point and a slope. Let's try to approximate e to the 0.1 using a linear approximation. A close point that we will choose is 0, 1, since we know that e to the 0 power is 1. That's our point. But this value is an under approximation because e to the 0.1 power is larger than e to the 0 power. So I know that to approximate e to the 0.1 power, it's going to be close to 1. But we know that 1 is an under approximation. So we're going to use the slope of our tangent line in order to get a better approximation. The slope of the tangent line, f prime of x, the derivative of e to the x, of course, is e to the x. We're going to evaluate when x equals 0. So f prime of 0, or e to the 0 power, of course, is 1. This will now allow us to come up with an equation of the line, at least when x equals 0. So when x equals 0, we get the equation y minus 1 is equal to e to the 0 power, which e to the 0 power, this right here, of course, is our slope, times x minus our x value, which in this case is 0. If we do that, we'll get y minus 1 is equal to x, which of course we could simplify to y equals x plus 1. Using this linear equation, we can now use this to try to evaluate what is e to the 0.1 power when x equals 0.1. So all we have to do is just substitute in 0.1 into our x, and we get that it's approximately 1.1. So we could say e to the 0.1 power is approximately 1.1, but it's definitely not to the 0.0001 accuracy. So the actual value of e to the 0.1 power is 1.10517, and our approximation is only accurate to 0.1 accuracy. All tangent line approximations can be written in the form of our approximation, and we're going to call this our first degree polynomial, or p sub 1 of x, is equal to a sub 1 of x plus a naught. A sub 1 and a naught are constants. We call this a first degree polynomial function since x is to the first degree. P sub n of x will be used to approximate any polynomial of n degrees. The problem with using a linear approximation is the further you move from a given point, the less accurate our approximation is, and it gets progressively less reliable. What would happen if we didn't use a line, but rather a quadratic function to approximate e to the 0.1? The approximation for a quadratic polynomial will have the form of p sub 2, because it's a second degree polynomial now, of a sub 2 times x squared plus a sub 1 of x plus a naught. This would give us a much more accurate approximation because we know that a curve of a polynomial will match the curve of an exponential function much better than a line. This is a little bit harder, but all we have to do is determine the coefficients and we will have a much better function to approximate e to the 0.1 power. So how do we do that? To find the second degree polynomial that approximates the value of our function, we will need to impose the following conditions. The value of our polynomial at 0 must equal the value of our function at 0. The derivative of our polynomial function at 0 must equal the derivative of our function at 0. And the second derivative of our polynomial function must equal the second derivative of our function at 0. So what is this really saying? The first one, our polynomial at 0 must equal our function at 0. There must be a value that we actually know. The second point, the derivative of the polynomial must equal the derivative of our function, just tells us that it must be going in the same direction. If our original function is increasing, our polynomial should also be increasing. If our original function is decreasing, then our polynomial should also be decreasing. The third point tells us that if our original function is concave upward or downward at 0, the polynomial function should have the same behavior as well. If we impose these conditions, we guarantee that our approximating function will, 1, be a point that's close to a point that we know. 2, it will have the same direction as our original function. And 3, it will have the same concavity as our original function. In essence, we know that our parabola will be as similar to the original function as possible, and it will be close to a point that we know. Note, in the above conditions, f of x is our original function, and we're using 0 since this is a point that we know that is close. If we were trying to evaluate e to the 1.1 power, of course we wouldn't be using 0, we would be using 1, because e to the 1 power is e, and that's a value that we know. Now, using our conditions, how do we find a naught, a sub 1, and a sub 2? Well, we know that our function f of x is e to the x power. We also know that our polynomial a sub 2 of x to the second power plus a sub 1 of x plus a naught is our polynomial. We're now going to just evaluate this at the point that we know, and the point that we know is 0. So we're going to substitute in 0 into all of our x's, and we're going to see what that equals. And so if we substitute in 0 into all of our x's, a sub 2 times 0 is 0, a sub 1 times 0 is 0, and we're left with a naught. And a naught must equal our original function at 0. And so a naught equals e to the 0 power, or a naught equals 1. We're now going to try to find a sub 1 now that we know that a naught is 1. So we know that the derivative when x equals 0 must equal the derivative of our original function when x equals 0. So f prime of x, which, if we find the derivative of our polynomial, will give us 2 a sub 2 of x plus a sub 1. And we also know that f prime of x is equal to e to the x. We're then going to evaluate this at 0 once again. If we substitute in 0, we're left just with 2 times a sub 2 times 0, which is 0, plus a1. Of course, that just leaves us with a1 equals e to the 0 power, which means a1 is 1. We're going to do this one more time for the second derivative. So we know that the second derivative of our polynomial at 0 is equal to the second derivative of our function at 0. The second derivative of our polynomial is 2 times a sub 2, and that's going to equal e to the x power when x equals 0. So if we substitute in 0, we get that 2 times a sub 2 is e to the 0 power, or 1, and that means that a sub 2 must be a half. We now know all the constants, and we could just substitute it into our polynomial, and we get that our second degree polynomial that will give us a good approximation will be 1/2 x squared plus x plus 1. Now, we could go ahead and approximate this by substituting in 0.1. If we substitute in 0.1 into all of our x's, we're going to get 1.105. Once again, we were trying to evaluate this to 0.001 accuracy. E to the 0.01 power is approximately 1.105, and the actual value is 1.10517 if we go to 5 decimal places. This is closer, but it's still not to 0.0001 accuracy. So what do? We try a third degree polynomial. We're going to use the exact same process, except now we're going to use a cubic function, because you should know cubic functions grow a lot faster than quadratic functions, and exponential functions grow a lot faster than polynomials. And so we want to get a polynomial that's going to grow similar to as fast as an exponential function to 0.0001 accuracy. Luckily for us, there's only one new term, and all the other terms stay the same. So for the sake of simplicity, I'm going to rewrite the polynomial as this. So I'm going to write it somewhat backwards. P sub 3 of x is our constant, plus a sub 1 of x, plus a sub 2 of x squared, plus a sub 3 of x cubed. Once again, we already know that a naught is 1. We already know that a sub 1 is 1. And we already know that a sub 2 is a half. So all we have to actually do is find a sub 3. Now, in order to find a sub 3, we're going to have to add another condition. This condition is that the third derivative of our polynomial should equal the third derivative of our original function when x equals 0, or when x equals the value that's close to the point that we know. So if the third derivative of our polynomial at 0 is equal to the third derivative of our function at 0, then we know that the third derivative of a sub 3 times x cubed is going to give us 6 times a sub 3. And the third derivative of e to the x, of course, is e to the x. We can then substitute in 0 for our x's, and we get that 6a sub 3 is equal to e to the 0 power, or 1, and a sub 3 must be 1/6. So all we have to do now is substitute in 1/6 into a sub 3. So our third degree polynomial is 1 plus x plus 1/2 x squared plus 1/6 x cubed. If we substitute in 0.1, we'll get 1 plus 0.1 plus 1/2 0.1 squared plus 1/6 0.1 cubed. And this gives us 1.10517. And we said e to the 0.1 power is approximately 1.10517, and it is to 0.00001 accuracy. And so now we have an incredibly accurate estimation for e to the 0.1 power using this polynomial. And this polynomial that we just created is called a Taylor polynomial. More specifically, in this case, it's called a Maclaurin polynomial. And we'll talk about the specifics of that in a second. So what do we do if we want to be even more accurate? Of course, we just get a higher degree polynomial. The higher degree our polynomial is, the more accurate our estimate is. Imagine if we could just get an infinite degree polynomial. In that case, we're going to get an exact value rather than an approximation. Of interesting note, a pattern occurs. Can you see what the pattern is? The nth degree polynomial of f of x equals e to x can be represented as 1 plus x plus 1/2 x to the second power plus 1/6 x to the third power plus 1/24 x to the fourth power, and so forth. So what would be the nth term? In this case, the nth term is 1 over n factorial times x to the nth power. So we could say that our polynomial of any degree, we could have a 5th degree polynomial, we could have a 100th degree polynomial, we could have a 1000th degree polynomial. All we have to do is follow this pattern until we get to n, which is the degree of our polynomial, which is approximately e to the x power. Other than having better accuracy, what's another advantage to having a larger n? A larger n would allow us to be further away from our known point, and it would still give us a good approximation. So let's go ahead and define a Taylor polynomial. The nth degree Taylor polynomial for f at c. Let f have n derivatives at c. Then p sub n of x, our nth degree polynomial, is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial times x minus c cubed plus so forth until you get to the nth degree. A special Taylor polynomial occurs when we're specifically at 0. When the value that we're trying to estimate is close to 0 and we know what the value is when x equals 0, it's called a Maclaurin polynomial. So when we use specifically 0, it's a Taylor polynomial that we specify as Maclaurin. So the nth degree Maclaurin polynomial for f is let f have n derivatives at c. Then the nth degree Maclaurin polynomial is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed plus so forth until you get to the nth degree. So let's go ahead and find the Maclaurin polynomial of 5th degree for f of x equals cosine of x. So if we just use this form of a Maclaurin polynomial, we should be able to evaluate this relatively quickly. So the first thing I'm going to do is I'm going to find cosine of 0, so that's going to be the value that we know, plus the derivative of cosine, which of course is negative sine, and we're going to evaluate that at 0, times x. We're going to find the second derivative at 0, which is negative cosine of 0 over 2 times x squared. We're going to find the third derivative of cosine, which is sine of x, at 0 over 6, which is 3 factorial, times x cubed, plus the fourth derivative of cosine, which is back to cosine of x at 0 over 4 factorial, or 24, times x to the fourth power, minus the fifth derivative, which is once again negative sine of x at 0 over 5 factorial, which is 120, times x to the fifth. If we evaluate all of these, you should know that sine of 0 is going to give us 0, and we're just left with 1 minus 1/2 x squared plus 1/24 x to the fourth. Now, if you think about what we just did, I came up with a polynomial that will allow me to approximate cosine close to 0, and it's going to do it very accurately. This polynomial can accurately estimate cosine for any x near 0. Let's go ahead and use our calculator and see if we can find what cosine of 0.1 is versus the fifth degree Maclaurin polynomial of cosine at 0.1. And what we see is this is incredibly accurate. Let's go ahead and find the Taylor polynomial for ln of x centered at 1. So obviously ln of 0 doesn't exist. So ln of 0 is negative infinity, and so we cannot use 0 for this. So there's no way for us to do a Maclaurin polynomial for ln of x. We can do a Taylor polynomial because Taylor polynomials could be centered anywhere. We say it's centered at the point that we can evaluate. So we know that ln of 1 is 0. So that's a point that we know. If we use our Taylor polynomial form of ln of x, we get the following. Let's go ahead and evaluate this by finding the derivatives of ln of x. We're going to get ln of c plus the derivative of ln of x is just 1 over x, or 1 over c, times x minus c, minus the derivative of 1 over x is negative 1 over x squared, times our 2 factorial times x minus c squared, plus the third derivative of ln of x is 2 over x cubed, times, and then our form of 1 over 3 factorial times x minus c cubed. And the fourth derivative ln of x is 6 over x to the fourth power. In this case, 6 over our center value to the fourth power times 4 factorial, times the quantity of x minus c to the fourth. So if we just substitute in our center value of 1, we're going to get the following. And then we could, of course, evaluate this. If you evaluate this, ln of 1 is 0. So that first term drops out, and we end up with x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the fourth power over 4. If we continue this process, can we say what the nth term is? And you should say that the nth term will be negative 1 to the n minus 1 power, because it is alternating, times x minus 1 to the nth power all over n. Which means that ln of x is the summation as n goes from 1 to infinity of negative 1 to the n minus 1 power times the quantity of x minus 1 to the nth power all over n. And if you look closely, you'll see that I say ln of x is equal, not approximately, because this is an infinite sum. This is an infinite degree polynomial, which tells us that it gives us the exact value of ln of x for any x near 0. So let's go ahead and find the fifth degree Maclaurin polynomial for a polynomial. So what happens if we try to find a Maclaurin polynomial for another polynomial? Well, in this case, if I follow the form, it's going to be 0 plus 2x plus 8 over 2 factorial x squared plus 0 over 3 factorial x cubed plus 96 over 4 factorial x to the fourth plus 0 over 5 factorial times x to the fifth. And if we evaluate that, we end up with our polynomial. Obviously, if we take a polynomial and we create another polynomial out of it, there's no polynomial that's going to mimic it better than itself. And so if we try to create a Maclaurin or a Taylor polynomial out of any polynomial, it just gives us back to the beginning. So how do we find the first 4 non-zero terms and the general term of the Maclaurin series for sine of x? Well, we're going to follow this form again. And this is a form that you definitely need to know and you need to commit to memory. It's really not that difficult, but it's something that you should understand. By the way, If you look at the first two terms, f of 0 plus f prime of 0 x, that's our linear approximation. Those first two terms, if we only do the first two terms, that always gives us the equation of our line. And so now what we're doing is we're just doing the same thing that we did in Calc AB when we were finding an equation of a line. We were using that to approximate a value. Now what we're doing is we're just expanding it so our approximation gets so much better. So our approximation becomes so much more accurate. So we're going to go ahead and approximate this for sine. So if we follow this form, I just have to keep following the derivative until I see a pattern. So we know that sine of x is our original function. Its derivative is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. And we're just going to continue that until we get to n. Of course, we're evaluating this at 0. So if we evaluate this at 0, what we see are the first four terms give us 0 plus x minus 0 minus x cubed over 6. And so every other term becomes 0. That being said, those are not my first four non-zero terms. So I have to keep going until I get four terms that are not 0. If I do that, I get x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040. The one thing that you should understand is for the first term here, this degree is 1, and it's actually over 1 factorial. This degree is 3 over 6, which 6 happens to be 3 factorial. This is x to the 5th, and 5 factorial happens to be 120. And then if we take 7 factorial, it actually gives me 5040. That being said, we could generalize this, and what we see is this function or this polynomial is alternating. So we're going to turn it into an alternating polynomial. So negative 1 to the n plus 1 power times, and what we see is all the exponents are odd. So our formula to make an odd value for any n is going to be 2n minus 1. And we know that that's also going to be our factorial for our denominator. So it becomes 2n minus 1 factorial in the denominator. And that right there gives us our first four terms as well as our general term. If we turn that into a summation, it's going to be sine of x equals, and once again I'm saying equals because I'm going to carry this to infinity, negative 1 to the nth power times x to the 2n plus 1 power all over 2n plus 1 factorial. And this will give us not only an approximation but an exact value for any x close to 0, which if you think about that is amazing. Since we know that sine of x is now equal to this Maclaurin polynomial of x minus x cubed over 3 factorial plus x to the 5th power over 5 factorial minus x to the 7th over 7 factorial, how would our Maclaurin series change and the nth term change if our function was sine of 3x rather than just sine of x? Well, what would happen is we would substitute all of our x's with 3x. So we end up with 3x minus 3x cubed over 6 plus 3x to the 5th over 120 minus 3x to the 7th over 5040. Or if we go to our general term, it's going to be negative 1 to the n plus 1th power. It's still going to be alternating. And it's going to be 3x to the 2n minus 1 power all over 2n minus 1 factorial. How would our Maclaurin series and nth term change if I multiply it times x? So let's say I want to find x times sine of 3x. Well, if you think about it, we know what sine of 3x is. It's the polynomial that we have above. So what would be x times this polynomial? Well, all I have to do is just multiply the entire polynomial times x. So if I multiply the entire polynomial times x, I'm going to get 3x squared minus the quantity of 3x cubed times x all over 6 times the quantity of 3x to the 5th times x over 120 minus the quantity of 3x to the 7th times x over 5040. Or for our general term, it's going to give us negative 1 to the n plus 1 power times 3 to the 2n minus 1 power times x to the 2n power, all over 2n minus 1 factorial. Okay, so see if you could write x times sine of 3x as a series. Well, that, of course, is just the summation as n goes from 0 to infinity of the nth term. Given that cosine is equal to 1 minus 1/2 x squared and so forth, what would be the first four non-zero terms and the general term of the Maclaurin series for cosine of x? Well, if we follow the pattern, what we see is all the exponents in the numerator are even. We saw that the exponents for sine of x were odd, and so it makes sense that the exponents for cosine of x would be even. And we see that the degree of the numerator becomes the factorial in the denominator. So let's go ahead and write cosine of x as a series. If we write it as a series, it's going to become the summation as n goes from 0 to infinity of negative 1 to the nth power times x to the 2nth power all over 2n factorial. Now you might ask, can't we just do a summation of the nth term? And the answer is yes. You just have to be careful what value you're starting at. So this value right here that we start at doesn't always start at 0. Sometimes it might start at 1. Sometimes it might start at some other value. And so you have to make sure that when you substitute in this first term, it gives you this first term here. If you don't do so, you may end up with the wrong summation. So let's go ahead and find the third degree Taylor polynomial for sine of x centered around pi over 2. So we've already done the Maclaurin polynomial for sine of x. Let's go ahead and do a Taylor polynomial centered around pi over 2. If we do so, we're going to get f of pi over 2 plus f prime of pi over 2 times x minus pi over 2. And we're just going to continue this pattern out for the rest of our polynomial. If you do so and substitute in pi over 2, we're going to get the following. We'll get 1 plus 0 minus 1 over 2 factorial times x minus pi over 2 squared minus 0. And this will give us 1 minus 1 half x minus pi over 2 squared. Now, I did ask you to find the third degree polynomial, and this is the third degree polynomial. It just happens that our third degree is 0. So this part of it becomes 0. If we were to go one more step out, it'd be 1 over 4 factorial times x minus pi over 2 to the fourth power, and that'd be a fourth degree polynomial. And we don't want that. We want a third degree, so this would be our third degree Taylor polynomial. So we're going to use this to approximate sine of 12 pi over 25. And if we do so, we're just going to substitute in 12 pi over 25 into this polynomial. And it's going to give us 1 minus pi squared over 5,000, or approximately 0.9980263. And the actual value of this, if we were to go a little bit further out or to evaluate this with a higher degree polynomial, we will see that it's going to be 0.9980268, and it's only off by these last two digits here, and so the first 6 digits are accurate. With that being said, we have a couple of special polynomials, and these are called hyperbolic functions. And so sine of h, when you have this h here, it means that it's hyperbolic. Now, sine of h, or this hyperbolic function, is actually not a trigonometric function. It's actually an exponential function, or a sum of a couple of exponential functions. The only reason why we have sine in there is because it follows the same form as sine does. And then this right here, we're going to call it cosine of h, or the hyperbolic cosine, and it gives us this function here. And the only reason we're using cosine of this hyperbolic function is because it follows the cosine form of our Maclaurin polynomial. And so because these follow our Maclaurin polynomial forms, we're going to use our sine and cosine names here, but these are actually not sine nor cosine in any way. They're actually just hyperbolic functions, and they're special functions that we do use and that you should know. So commit these to memory, and if you know these, then you should be in good shape. Well, thanks for watching. I hope this was helpful.